In this video, I wanted to talk about ball and roller bearings. So in the PE handbook, the key word is going to be bearings, and there's a little section on them, and there's two subsections to that sort of. There is the ball and roller bearings, and then there's also another section about journal bearings. But in this video, I just want to go over ball and roller bearings. So the main equation for this is C, which is the minimum required basic load rating, equals P, which is the design radial load, times L, which is the design life in millions of revolutions, to its exponent 1 over A. And A depends on whether it's a ball bearing or a roller bearing. So C is the minimum required basic load rating. P is going to be your design radial load. An emphasis on the radial load. We'll get to that in a little bit. L is the design life. That's going to be in millions of revolutions. And then the A here for ball bearings is going to be 3. And it's going to be 10 over 3 for roller bearings. Another thing this equation is called is the bearing life regression equation. Okay, so I underlined this radial load here because you can have bearings sometimes that have a thrust load in addition to radial load, and you actually can't directly use this equation with that. You have to find an equivalent radial load. And so to do that, the formula of the equivalent radial load is x times v times f sub r plus y times f sub a. So there's a lot of variables in this equation. So like I said, this is the equivalent radial load. And then I'm gonna say what these forces are first, because those are easy. This is the radial load. This is, or maybe we should call that like the nominal radial load. So this is the radial load the bearing is actually carrying. Then the axial load, another word for that is the thrust. And so the two of those combined along with these modifiers give you the equivalent radial load. Okay, so this V here is, I don't really know if that has a name, but V will equal 1 if the inner ring is spinning. And V will be 1.2 if the outer ring is spinning. Okay. Now for these x and y terms, it's a little bit more complicated. There's a little bit more to it. So there's actually a third variable we need to bring in, which they call E, and the E is equal to 0.513 times your nominal axial load divided by C naught. The C naught is called your what do they call it? The basic static load rating from the bearing catalog. So this C up here is your basic dynamic load rating. This is your basic static load rating. That's why it's different. And then this is going to be to the 0.236 power. So if your nominal axial load divided by V times your nominal radial load is greater than E, then X equals 0.56 and Y equals 0.84 times F sub A, so your axial load divided by, again, that static load rating, and this is going to be to the negative 0.247 powered. Okay, but if F sub A over V, F sub R is less than or equal to E, then X equals 1 and Y equals 0. There is another equation on here. I don't know if it's used very often. It's F sub big R. It's your catalog radial rating in either pounds or kilonewtons. So that's equal to S sub D, which is your required radial design load, to the N sub D, which is, or sorry, not to the power of, it's times N sub D divided by N sub R. So N sub D is the required design speed, and N sub R is the catalog rated speed. And that thing is going to be to the 1 over A. This is the same A as before. Another way of writing this is F sub D times L sub D, where L is the required design life in hours, times N sub D divided by L sub R, which is the catalog rated life in hours, times N sub R, to the 1 over A. I've never used this equation before. I've never come across a problem that I've needed to use it, but it's in the handbook, so I just thought I would write it out. But yeah, so I have an example problem here to go through. So a single row deep groove ball bearing supports a shaft operating at 1200 RPM. The shaft is expected to operate for 25,000 hours. The bearing is subjected to a radial load of 5.5 kilonewtons and an axial load of 2 kilonewtons. The inner ring rotates while the outer ring is stationary. The dynamic load rating is C sub 10 equals 42 kilonewtons. This is the same C as is up here. For this loading, E is 0.3. So we don't need to solve for E, which is kind of nice because it is a little bit of a messy, or it can be a little bit of a messy equation. So we're asked to calculate the equivalent dynamic bearing load, calculate the required life in millions of revolutions, calculate the rated life, and that would also be millions of revolutions. And then we're asked, does this bearing satisfy the required life? Okay, so for part A, we're going to use this equation here. So the equivalent radial load is going to be equal to X times V times F sub R, the radial load, plus Y times S sub A. So we know V is going to be 1 because our inner ring is rotating. So now let's take a look at, try to figure out which case, which one of these two cases we're going to be in. So F sub A divided by V times S sub R is, what is our axial load is 2, going to be divided by 1 times 5.5. So it's going to be 0.36 repeated. So 0.3636 is greater than 0.3, which is, remember, that's our E. So since that's greater, we have that x equals 0.56 and y equals 0.84 times the axial load divided by the static rated life to the negative 0.247 power. Okay, so it didn't actually give us the C naught, so we're going to have to solve for that, and the only way to solve for that is using the equation for E. So we have the E is 0.513 times F sub A over C naught to the 0.236 power. We can actually just solve for this ratio and then plug that in up there. So we have 0.3 divided by 0.513. That's going to be to the 1 over 0.236 power equals FA over C naught. So that's going to be 0.10297. So then our y is going to be 0.84 times 0.10297 to the negative 0.247. Which is 1.473. Okay, so now we can go ahead and solve for our equivalent dynamic load or equivalent radial load, however you want to say that. So we're going to have x is 0.56 times v is 1 times our radial load, which was 5.5 kilonewtons. We're going to add to that 1.473 times 2 kilonewtons, which is our axial load. So that's going to come to be 6.03 kilonewtons. So this is the equivalent radial load that the bearing is subjected to based on the actual radial load and the axial load that's applied to it. Okay, now we're asked to calculate the required life in millions of revolutions. So the required life is basically asking how many cycles does it need to last? How many millions of cycles does it need to last to fulfill this 25,000 hours at 12,000 RPM? So we start with 12,000 revolutions per minute. We convert that to revolutions per hour, so times 60 minutes in an hour, and then times 25,000 hours. It's going to be 1,800 million revolutions. So that's how many cycles this bearing needs to last in order to last the full 25,000 hours at 1200 RPM. So now we're going to calculate the rated load, the rated life. So that's going to be using this equation right here. So C equals P times L to the 1 over A. And we're trying to solve for this L here. So if we rearrange this, we'll have L equals C over P to the A. So this C was given to us. That was the 42 kilonewtons. And P, remember this is the equivalent radial load, which we just solved for. So 6.03 kilonewtons. And then A for remember this is a ball bearing. So the A for a ball bearing is going to be 3. So that comes to 337.91. And this is going to be in millions of revolutions. Okay, so then D, does this bearing satisfy the required life? So our required life is that it needs to last 1,800 million revolutions, but our rated life is only 337.91 million revolutions. So the answer is going to be no. And the reason is that the rated life is less than the required life. So this bearing will not survive this application, and it would need to be redesigned in order to do so. But yeah, these bearing problems generally aren't going to be this involved. In fact, I haven't seen one in any of the practice exams I've taken that have even used anything other than this equation here. But yeah, as long as you just know where to look and know how to apply these equations, you should be good.